In this video, we're going to introduce you to the concepts of impulse and momentum, which are closely tied together. So just like we did with Ewok, when we derived it from Newton's second law. So we're going to start with Newton's second law and start with the idea that we understand changes to the motions of objects, which is what we describe as acceleration, as due to a net force and proportional to the inertial mass of that object. So when we derived Ewok, what we were looking at is how the net force and the displacement, delta x, together caused a change in the motion. And we saw that that produced a change in the kinetic energy of that object. With impulse and momentum, we're going to look at the time dependence of a net force. So when we apply a net force on an object for a certain period of time, instead of having a change in kinetic energy, we're going to experience what we call a change in momentum. Now, let's look at how we derive this. So we can describe, now let me because momentum is a vector quantity, I'm going to put my vector arrows in here just to designate the vector quantities. We can describe an acceleration as a change in velocity of an object over a period of time, where velocity is the vector quantity and time is a scalar. Now, if we multiply both sides by delta t, what we see is, and I'm going to write this in different colors here, a net force, which is a vector quantity, multiplied by the amount of time over which that net force is exerted, is equal to the mass of the object times the object's change in velocity. Now notice, this is a net force applied to an object. So we're looking at the change in momentum of an object due to a net force over a certain period of time. Now this left side, the net force times the amount of time over which that net force is exerted, is what we call an impulse on that object. And since it's a vector quantity force, net force, times a scalar quantity time, impulse, which is designated as a capital J, sometimes it's designated as capital I, but more often capital J, it is a vector quantity. So the impulse J exerted on an object is the net force on that object with direction accounted for times the amount of time over which that force is exerted. Now if we look at the other side, this is an equality here. This mass times the change in velocity is what we give the name a change in P, or change in momentum. Oops. Of an object. Where momentum, we use the symbol P, and that's also a vector quantity because a velocity or a change in velocity is a vector quantity multiplied by mass, which is a scalar, and we get a vector quantity delta P. So the impulse on an object is equal to a change in momentum of that object. Now how do we get change in momentum from here? Well, m times delta V would be m times V final minus V initial. And if I distribute this out, this is m V final minus m V initial. And this is what we describe as the momentum of the object, momentum final in this case, and momentum initial. So the momentum of an object is a vector quantity, and it's equal to the mass of that object times its velocity at any given point in time. And momentum is a vector quantity. So the one thing I want to make a stress of here is oftentimes when people are learning about momentum and impulse, they think they're totally separate things. But remember, this is an equality here. So the impulse on an object is the change in momentum of that object. So they are really one and the same, but we describe impulse primarily in terms of the net force and the time, and we describe momentum primarily in terms of the mass and the change in velocity of that object. Now, let's look at the units just to make sure that the units come out. When we have force times time, and we'll do a unit analysis over here, we have newtons times seconds. When we do mass times velocity, so these are going to be the same. Let's do this over here. We have a kilogram times a meter per second. So unit analysis should come out. So let's see, can we get this to be the same as this? Well, we know a newton is a kilogram meter per second squared. So this is kilogram meter per second squared times a second. And in this case, the second cancels with the second squared, and we're left with standard units of kilogram meters per second, which, if we look, is the same. So impulse and momentum are derived from Newton's second law. They're ways of expressing the change of the motion of an object in terms of the force and the time over which it's applied. Impulse we typically describe as force times time. It's a vector quantity. And then momentum we typically describe as the mass times the velocity, or change momentum as the mass times the final velocity minus the mass times the initial velocity. Now be very careful, because this is a vector, directions count. So anytime you're doing a problem with impulse and momentum, you have to define your reference point in terms of what's positive, what's negative, and you have to account for directions in terms of your velocity as positive or negative. Otherwise, you're going to have sign mistakes that are going to end up giving you the wrong information. But that is an introduction to impulse, force times time, and change in momentum, mv final minus mv initial, where m times v is defined as the momentum of an object at any given velocity.